Hello all. Today we will be discussing on three topics: PCM, DPCM and delta modulation. First, let us go through the topics. First topic, PCM, pulse code modulation. PCM, it is to digitally represent sampled analog signal. So we can say the PCM is a method used to convert an analog signal to a digital signal, and here we use only binary forms, which means it has only two possible states, high and low, or 1 and 0. In PCM, a message signal is represented by a sequence of coded pulses, which is accomplished by representing the signal in discrete form in both time and amplitude. So now let's go through the basic elements of PCM system, that is transmitter, transmission path and receiver. So these three are the block diagrams of the transmitter, transmission path and receiver of the PCM system. And have a look at this. We have a low pass filter in front of the sampler here. So first basic operation of a transmitter in PCM system is sampling. In sampling, the incoming message signal is sampled with a train of narrow rectangular pulses so that we can closely approximate the instantaneous sampling process. And according to the sampling theorem, we know that sampling frequency must be greater than twice the maximum frequency of the input message signal. And here, this is also to ensure perfect reconstruction of the message signal at the receiver. But in practice, a low-pass anti-aliasing filter is used at the front end of the sampler to exclude frequencies greater than FM, which means maximum frequency of the message signal. And the application of the sampling permits the reduction of continuously varying message signal to a limited number of discrete values per second. The next one is quantization. Second operation of the transmitter is quantization. The sampled signal has to be quantized, and after that it provides a new representation of the signal that is discrete in both time and amplitude. For quantization, we can use either a uniform quantizer or a non-uniform quantizer. So what is a uniform quantization? In uniform quantization, the quantization levels are uniformly spaced, whereas in non-uniform quantization, the quantization levels are unequal and mostly the relation between them is logarithmic. So here we use a non-uniform quantizer, and the use of non-uniform quantizer is equivalent to passing the baseband signal through a compressor and then the output of the compressor to a uniform quantizer. And here a particular form of compression law is used for this compression thing, and that law is mu law, which is defined by before telling about law, let me tell you these two diagrams. First one is the plot for mu law and second one is the plot for A law, which we'll be discussing after mu law. So mu law, which is defined by mod V is equal to log of 1 plus mu mod m by log of 1 plus mu. And in the previous slide we have plotted the mu law for three different values of mu, and for let me say for mu is equal to 0, It represents the uniform quantization. And the reciprocal slope of compression curve, it can be represented by taking the derivative of mod m with respect to mod v, as shown in this equation here. Now there is another compression law known as A law. Here it is defined by mod v is equal to A mod m by 1 plus log A for 0 less than or equal to mod m less than or equal to 1 by A, and 1 plus log of A mod m by 1 plus log A for 1 by A less than or equal to mod m less than or equal to 1. And we have got that this A law in the previous slide, and here A is equal to 1 represents the uniform quantization. The reciprocal slope of compression curve is same as before, derivative of mod m with respect to mod v, and equation is shown here. Next one is encoding. Encoding is the process to translate the discrete set of sample values to a more appropriate form of signal. And some terms we used in here are code, code element, code word. What is a code? Any plan for representing each of the discrete set of values as a particular arrangement of discrete events is known as code. And one of the discrete events in a code is known as code element or a symbol. And we can say the presence or absence of symbol, presence or absence of a pulse as a symbol. And the third one is code word. Particular arrangement of symbols used in a code to represent a single value of the discrete set is known as code word or character. And we can say binary code, it has two symbols, 0 or 1. And ternary code has 3 symbols. And the maximum advantage over the effects of noise in a transmission medium is to obtain by using binary code. Is obtained by as binary symbol can withstand a relatively high level of noise and it is easy to regenerate it. Now let's go to the next one. Line codes. Line codes can be used for the electrical representation of a binary data stream. We have to learn about 5 important line codes: unipolar non-return to zero signaling, polar non-return to zero signaling, unipolar return to zero signaling, bipolar return to zero signaling, and finally split phase or Manchester code. And here we represent each of these 5 line codes here for the binary data 0110 1001. So we can say about first one, unipolar non-return to zero signaling. Here the symbol 1 is represented by transmitting a pulse of amplitude A for the duration of the symbol, and the symbol 0 is represented by switching off the pulse. Second one is polar non-return to zero signaling. Here the ones and zeros are represented using by transmitting the pulses of amplitude plus A and minus A. Third one is unipolar return to zero signaling. Here the ones are represented by pulse of amplitude A and a half symbol width. Zero symbols are represented using no or by transmitting no pulse. The fourth one is bipolar return to zero signaling. Here the plus and minus pulses of equal amplitude represents the symbol 1 and they are used alternatively. And to represent the zero symbol, we transmit no pulse. And this bipolar return to zero signaling is also known as alternate mark inversion. And finally, the fifth one is split phase or Manchester code. One is here the symbol 1 is represented by a positive pulse of amplitude A followed by a negative pulse of amplitude minus A, both pulse being half symbol wide. And the 0 symbol is also represented the same way, but there is a change here. It is polarities of these two symbols are reversed here. Now let's go through the basic operation of receiver of a PCM system, pulse code modulation. The most important feature of PCM system lies in the ability to control the effects of noise and distortion produced by transmitting a PCM signal through a channel, and this can be accomplished by reconstructing the PCM signal by means of a regenerative repeater. And this regenerative repeater is located at sufficiently close spacing along the transmission route. This regenerative repeater has three basic functions. First one is equalizing, second one timing, and third one decision making. And here we have shown the block diagram of the regenerative repeater also. First, the equalizer. The equalizer shapes the received pulses so as to compensate the effects of amplitude and phase distortions produced. Timing provides a periodic pulse train derived from received pulses for sampling the equalized pulses at the instant of time where SNR is maximum, that is signal to noise ratio is maximum. Each sample so extracted is compared to a predetermined threshold in the decision making device. So in each interval the decision is made, that is 1 or 0, but it is according to the threshold, that is if our extracted sample exceeds the threshold or not. If it exceeds the threshold, then a clean 1 is transmitted to the next repeater, otherwise a clean 0 is transmitted. And the two reasons, the regenerated signal departs from original signal for two main reasons. Reason 1, the unavoidable presence of channel noise and interference causes the repeater to make wrong decisions occasionally, thereby introducing bit errors into the regenerated signal. Second one, if the spacing between received pulses deviates from its assigned position, a jitter, that is a deviation, is introduced into the regenerated pulse position, thereby causing distortion. Next is decoding. It involves generating a pulse, the amplitude of which is the linear sum of all the pulses in the code word. And finally we have filtering, that is we have to recover the message signal and it can be done by with the help of a low pass reconstruction filter with a cutoff frequency which is equal to the maximum frequency of the message signal. Assuming the transmission path is error free, the recovered signal includes no noise. That is, there is no noise in the recovered signal, but there is an exception. There will be a distortion due to the quantization. So we can now go through the representation, some of the equations. Signaling rate R is equal to the product of Fs and R, where Fs is the sampling rate and R is the number of bits per sample. And we can represent the bandwidth in terms of sampling rate, that is bandwidth is R by 2, that is sampling rate divided by 2. Now the signal to quantization noise ratio SNR is equal to P by sigma Q, where P is the signal power and sigma Q is the variance of quantization error, and it is given as 1 by 3 times M maximum square by 2 raised to 2R, where M maximum is the dynamic range of the quantizer. So finally we get SNR is equal to 3P by M maximum square into 2 raised to 2r. Now next topic is differential pulse code modulation. Differential pulse code modulation, DPCM. It is a signal encoder that uses the baseline of PCM but adds some functionalities based on the prediction of the samples of the signal. Here the input can be analog or digital. When a voice or video signal is sampled at a rate slightly higher than the Nyquist rate that we used in PCM, the output or the sample signal we got exhibit a high degree of correlation between adjacent samples, and the signal does not change rapidly from one sample to the next. The encoded signal contains redundant informations, which means the encoded signal, that is signal we get, will contain redundant information, that is the output of PCM. So now we have to remove this redundancy, and this is the basic idea of DPCM. Now consider a baseband signal M of t at the rate M of t, and sample this M of t at the rate Fs is equal to 1 by Ts. We get a sequence M of n with sampling period Ts. If we know past behavior of the signal up to some extent, we can make predictions to estimate the future value. And the fact that it is possible to predict the future values of the signal M of t provides a motivation for the differential quantization scheme. And here is transmitter and receiver of the DPCM. This is a modulator which here is a modulator which contains the comparator, quantizer, and the prediction. Here we have a comparator, quantizer, and we have a prediction filter. Now let's see the input signal of the quantizer, which we seen in the previous slide. E of n is equal to M of n is minus M cap of n. M of n is the unquantized input sample and M cap of n is the prediction. E of n is the prediction error. And we will get a quantizer output as EQ of n. E of n plus Q of n. Q of n is the quantization error. EQ of n is the quantizer output. And the prediction filter input is MQ of n, and it is given as M cap of n plus EQ of n. That is, it is equal to the sum of the quantizer output and the prediction value. By making some substitutions, we will get MQ of n is equal to M cap of n plus E of n plus Q of n, and rearranging with the previous equations, we will get MQ of n is equal to M of n plus Q of n. Now let's get through the processing gain. Here the output signal to noise ratio of the DPCM is equal to SNR is equal to sigma m squared by sigma q squared, where sigma m square is the variance of original input sample M of n, and sigma q square is the variance of the quantization error. We can rewrite this SNR as SNR is equal to sigma m square by sigma e square into sigma e square by sigma q square is equal to GP into SNR. So SNRQ is the signal to quantization noise ratio, which is equal to sigma e square by sigma q square. So the remaining one is GP, which is the processing gain. GP is equal to sigma m square by sigma e square. And now the final topic that we have is delta modulation. Delta modulation, it is a technique where we can convert analog signal to digital signal or a digital signal to a analog signal. It is used for the transmission of voice information where quality is not of primary importance. In delta modulation, the message signal is oversampled to increase the correlation between adjacent samples of signal. And in its basic form, the delta modulation provides a staircase approximation to the oversampled version of the message signal. And the difference between the input and the approximation is quantized into two levels, plus delta or minus delta, corresponding to the positive and negative approximation. If the approximation lies below the sampling epoch, then it is increased by delta, and if it lies below the signal, then it is diminished by delta. And this is illustration of the staircase approximation. So now let's denote M denote the input message signal and MQ of T denote its staircase approximation. So we have a sampling equation. M of n is equal to M of NTS, where n is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3. Here Ts is the sampling period, and M of NTS is a sample of the signal M of T at T is equal to NTS. Formalizing the basic principles of delta modulation, we get the following set of equations. E of n is equal to M of n minus MQ of n minus 1. Here E of n is the error signal, and it is the difference between the present sample M of n and the latest approximation MQ of n minus 1. And the other next one is EQ is equal to delta signum function E of n. EQ of n is the quantized version of E of n, and we have used the signum function here. In the output of the quantizer, MQ of n is given as MQ of n minus 1 plus EQ of n. Now we know that Dm, in Dm, the rate of information transmission is equal to sampling. Now, the delta modulation is generated by applying the sampled version of incoming message signal to a modulator, which consists of a comparator, quantizer, and an accumulator. The Z inverse block in this accumulator is unit delay, which is equal to the sampling period, one sampling period. The comparator computes the difference between two inputs, and the quantizer consists of a hard limiter with an input-output relation that is a scaled version of signum function. And the output of the quantizer is given to accumulator to the result of the accumulator we get is MQ of n is equal to delta sigma I is equal to 1 to n signum function E of I is equal to sigma I is equal to 1 to n EQ of I. At the sampling instant NTS, the accumulator increments the approximation by plus or minus delta, that is M of n greater than MQ of n. We get, that is, if M of n is greater than MQ of n, that is input signal is greater than the approximation, accumulator increments the approximation by plus delta, otherwise it will be minus delta. Now there are two quantization errors for which the delta modulation gets subjected to. One is slope overload distortion and the other is granular noise. Now let us consider the first one. Slope overload distortion. Here consider the equation or the output of the quantizer. MQ of n is equal to M of n plus Q of n. The input to the quantizer is E of n is equal to M of n minus M of n minus 1 minus Q of n minus 1. We got this from the previous equation. If we consider the maximum slope of the original input waveform, it is clear that in order for the sequence of samples MQ of n to increase as fast as the input sequence of samples m of n in a region of maximum slope of m of t, it has to satisfy a condition that is given below: delta Ts greater than or equal to maximum of the derivative of m of t with respect to time. Now, otherwise, what will happen? We find that the step size is too small for the staircase approximation mq of t to follow a steep. Otherwise, we find that the step size is too small for the staircase approximation mq of t to follow a steep segment of the original signal m of t, which results that mq of t falls behind m of t as shown in this figure. And this condition is known as slope overload, and the error is known as slope overload distortion. And the next error is second one, granular noise. It occurs when the step size delta is too large relative to the local slope characteristics of the input waveform m of t, thereby causing staircase approximation mq of t to hunt around a relatively flat segment of the input waveform. And this is analogous to the noise in pulse code modulation. So next, see delta sigma modulation, the advanced form of delta modulation. This is to overcome the drawbacks of delta modulation. The quantizer input in the conventional form of delta modulation may be viewed as an approximation to the derivative of incoming message signal. This results in a drawback in delta modulation, that is, there will be the presence of noise. We can overcome this drawback by integrating the message signal prior to delta modulation, and we can say a delta modulation scheme that incorporates integration as its input is termed as delta sigma modulation. So now we have seen, or we have discussed, the three topics: PCM, DPCM and delta modulation. So thank you.